Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today we continue our class on reactive power control. So we have discussed about the relationship between the power transfer from the sending end to the receiving end, and the relationship between the voltage, current, and power. So today we look at the calculation of sending and receiving voltage in terms of power and reactive power. So we have source and the impedance here, and then we have load. So we have the voltage here. So we have source plus minus in terms of E, and then the current flows here. So we have the voltage drop, and we have this is at the terminal, receiving end terminal, so we have V. So what we have here, we have a phasor diagram of these conditions. So this is what we can see in terms of your sending end and receiving end. So normally we refer at our receiving end voltage as at the asalan, meaning that if we as a refer here, so that's why your V normally at the angles of 0, okay, because we want to make sure that it maintain your V at the angles of 0. And then so our excitation, normally we have angle of theta here. So what we can see here, this is the phasor for the transmission of power system through the R as well as your X. So we have V and we have excitation phasor. So we can see here that we have current there. When the current flow, and then we have voltage drop here. So normally your current will be angle with the voltage is in terms of pi. Okay, so phi. And then what we can see here that the voltage drop, this equals to IR, right? IR and plus X. So meaning that this is your IR, and this one is IX. The reflex of the impedance here. So what we can see, there is a lot of point here. We have A, B, C, D, and then we have G here. So this one basically we can see that the how we create or how we derive the equations. So from the figure just now, we can see that we can use theorem Pythagoras for E square equals to V plus V theta V square plus theta V. So let me look at this, your V, this is your E, right? So this is your V. Okay, and then just now you have here, you have theta V. So here is your, we call it delta V. So from here we can see this is 90 degrees. Okay, and then you have theta here, this one is your E. Okay, this is how you derive. We just using the theorem Pythagoras, right? E square equals to V plus the theta V square plus your as the y axis here, theta V square. And from the figure just now, we can see that there is a we can see there is point that we can see we can derive and express in terms of Euler technique. So you have delta V equals to IR cos pi plus XI sin pi. So just represent this thing into this equation. And from here you can see there is some, if you refer back, because I'm using the PowerPoint recording, you cannot refer back to the figure. So basically you can see that you can derive from delta V square here, it can be representing by XI cos pi minus IR sin pi. And this thing basically you can rearrange back. You know that our P and Q, normally P equals to cos pi plus sine pi, cos pi, IR cos pi, right? And then for Q normally I sine pi. Okay, so basically P equals to, if you remember the equation, P equals to VI cos pi, right? So I cos pi equals to P over V. That's why you get RP over V. So similar for Q. The Q is, sorry, I don't have any tools. Is VI sine pi, right? Sine pi, and then sine pi, I sine pi equals to Q over V. That's why you get RP over V plus XQ over V. This one is just the equation, the original equation. Similar with this equation, basically you can get XP over V minus RQ over V square. And then we know already that this is our delta V is RP plus XQ over V, and your theta V XP minus RQ over B. So basically, normally when we derive in power system, normally we refer back at that we assume that some part is much lesser or less than these two parts normally, so we can ignore the other parts. Normally we ignore these things. At the end of the day, you get this value, so because you assume this one is much lesser, it's not give you much impact to the equation. So what left is V plus RP plus XQ divided by R square. So this is what you get in terms of this equation. And we know when we rearrange this thing, you get E minus V is delta V basically. So because this is just a simple notation, so RP plus XQ divided by V got delta V. So hence the arithmetic difference between the voltage is given approximately by RP plus XQ divided by V. And surely when we deal with power system, normally we assume that our R is much lesser than X, so that's why you can ignore this thing. So at the end of the day, you get your E minus V equals to XQ divided by V. So this is the proof that if we want to control the voltage or you want to control the Q, so it's true because the voltage is only depend on Q. This is just the conclusion that we get here. Okay, so this is how we derive. Okay, and then we move to the operation of generator on infinite bus. So what happen if we have in terms of infinite bus? So most synchronous machine are connected to large interconnected arithmetic power system networks. These networks have an important characteristic that the system voltage at the point of contact is constant in magnitude, phase angle, and frequency. Such a point in power system is referred as infinite bus. So we refer that one is as infinite bus, infinite system of generation. The voltage at the generator bus will not be altered by changes in the generator operating condition. For example, 600 megawatt generator is removed from 30,000 megawatt system. The difference in voltage frequency cost is very slight. So this is what we talk about when we connect your generator with the infinite bus. Okay, just now we just connect our sending with the receiving end voltage, we just refer to simple load. So now we assume that this is an infinite bus. Okay, so we have our XD here. Again, we have voltage drop. So you have I, to get I is E minus V divided by JXD, since we assume that this value is only have X, don't have any R. So JXD normally is about 90 degree, right? So when you convert JXD into the absolute value or the value with the magnitude and angle, you get the J 90 degrees, XD 90 degrees. So when you do the subtract, this one you can separate it. So you get theta minus 90 degrees. So this one 0 minus 90 degree, because in phasor, when you do division, it is minus. Okay, so you get I equals to E delta theta minus, this one have ada kurungan lah. Okay. And the power P equals to real VI square, VI conjugate, remember. So you times V with this I, you get this value. And again, you can use Euler, or you can use the expansion of A plus B concept, because this one is the cos theta, because this is consists of cos and sine, right? So for for real power, we just consider of cos. So that's why cos 90 minus theta, V equals 90 degree minus XD, divided by XD. This one, because cos 90, you can get how much? I think cos 90 is 0. So that's why it's will cancel. So at the end of the day, we assume that our this one you need to do the cos, you need to do the expansion, if you remember. So you have cos A minus B, right? So in exam, this one is just a simplification. So in exam, you need to derive cos A cos B minus sin A sin B, that one. So I think that's why at the end of the day you get this value for the P. So P equals to EV over XD sin theta. Similar for the Q. So we impose the sine function. So at the end of the day, because this one cannot be cancelled, because your sine 90 degrees is 1, right? So that's one you have here. So again, you need to enforce this thing, sin A cos B cos A sin A. I think you need to refer to the your notes. Please, in your examination, your result must be elaborated more. Okay, it's not just simplification as this derivation. You kena kembangkan lah. So at the end of the day, you dapat Q equals to EV cos theta divided by XD minus V square divided by XD. Okay, let's take example. So the example, I think I will not discuss, because you can see this example exactly at my module. So please refer to my module. Okay, similar, this one is page 65. Okay, I think that's all for today. So next we will look at the methods of voltage control. I think that's all for today. See you next class. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much.